Hi, I'm Samath and I'm going to be talking about state machines and coroutines. It is a elegant architecture to build complex GUIs and other UIs. So this is just a rough draft of the talk, mostly to see how it goes and to see how long it takes. And I would like to keep improving on this. So let's start by trying to build a simple GUI. So the first feature that we'll have is we'll be able to click and drag shape groups around. So in this case, a shape group is just any number of shapes that are grouped together. So in this case, there are two. One has two shapes and one has one shape. The next feature that we want to add is double clicking to select a shape group. So whenever we double click on a shape group, it would get selected. In this case, it's highlighted with a white border. The next feature is once the shape group is selected, we want to click and drag around individual shapes within that. And if we double click on a shape, we want the shape to get selected. So here once this shape group is selected, we can see that you can click and drag to move shape groups around, and double clicking gives it a dark outline, which means that that shape is selected. So this is the very simple GUI that we want to start off by building. So uh, yeah, let's do the first feature, which is drag to move. So this is a very simple breakdown of the application. We have inputs, we have all the groups, and we have a single active group index, which is an optional index. So on every frame, we'll handle mouse inputs, and if the mouse button is clicked, we'll check if we're clicking on the group index. So this get group index will check the mouse position and see if there's any group within that. And if the mouse button is down and we have a group index clicked, then we will set the group position. So that's fairly straightforward. Is clicked is set to true on the frame that the mouse was clicked, and from the next frame onwards it's set to false. So now if we're going to go to the next feature, which would be double click to select, so then we'll have to add two extra uh, parameters to the struct, which would be last click ticks, which is to find out when was the last time that we clicked, and last group index, which is to see which was the group that we clicked on last time. Because if we double click on two separate groups, we don't want both to be, I mean, we don't want either to be selected. And also if it takes too long between clicks, we don't want to trigger that as a double click. So here, this is just updating the inputs, and you can see it's already become a little bit more complicated because suddenly we have to take care of some amount of state, right? So again, we set the active group index to new index, and we check whether the previous value of group index and the current value are same, and whether the timing is correct. And then we set the group active, and similarly group position moves. So if we keep following down this road, we see that there's a certain structure that emerges, which is we keep checking if there's an active group, if that group has an active shape, if that shape has an active vertex, and so on. So in each case, we'll have to check the else and the else, and this would be the structure that eventually the application would get to, even for this seemingly simple use case. So uh, doing this would be the naive way of building a GUI. So some of the drawbacks are there are very unclear state transitions, which means that uh, how do we go from moving a vertex to moving a group, or how do we check when we are moving a shape, or etc. How do we know when state moves from one state to another? Secondly is where to write code. So once this gets a lot more complex, it becomes unclear as to where the code needs to be written, right? So if there's a certain feature that we need to add, you will have to figure out exactly where within this large bracket does the new code go, because you're looking for a certain specific state of each of these variables. We want all of them to be in a certain way when the new feature is added, and to keep that in mind becomes really hard. Similarly, there's a lot of mental memory overhead, which means that we always need to know while reading the code. Like over here, it's obviously compressed, but in a more advanced use case, you would have to keep always knowing which are the variables that are true or are false or are null, and then what should happen in those cases. So while developing it the first time around, it's easy, but once we go in later, since all of that information is not explicitly stored anywhere, it's implicitly stored within all of these state variables. You have to always keep in mind everything that's there before you can make any changes. So making changes becomes very slow because there's a lot of mental overhead. Some of the positives are it's relatively simple. So if we go back to the first example, if you just want things to move around, again, it's very simple. And even though the code is nested and complex, it's actually fairly straightforward to see what's happening, even if it's hard to understand and debug. Uh, you could argue that it's more robust because since you're checking every single case, uh, there is if you're ever in a case where you shouldn't be, you can always tag that or mark it as unreachable. So for example, if you are never supposed to have an active shape index, inactive shape index, then this else tag could be an unreachable, and then in some sense a lot more branches of the code are covered. So a lot more states are taken care of. And here when I say state, I mean possible configuration of all of these different variables. In some sense, it's clean because I come from a web development background, and in that there is a huge emphasis on not storing extra variables. So why I would say that this can be considered clean, or why I used to consider it clean, is because there is no explicitly stored state value. Right? The state is implicitly stored within this, and since we are always navigating through this tree to figure out what exactly state our application is in, it means that you're not explicitly storing it elsewhere, and there is no chance of those two going out of sync, at least in some theoretical sense. So uh, that would be one of the things that you could say it's clean. So this sounds a bit like a dummy that I'm showing this code just to scapegoat, but I have actually written fairly complicated GUIs in this, including some vector editors with Bezier splines and things like that, where it is fairly complicated, and it's possible to do it this way, but it just takes a long time. And more than anything, this is the biggest problem, right? These two, there sometimes if you want to add a new feature and you go in a few months later, you're not really sure where the code should go, and again, this overhead is a lot. So as you can say, I've been using the word state a lot. So if you let go of some theoretical purity, then you can improve the state a lot, right? So here what we would do is we would make a state machine. So that means that the UI would be handled based on what the current state is. So in our simple example, you have these 7 states. So if you take a subgroup of that, when the application is a neutral state, if you click on a group, it goes to group click. Then you either double click or you drag or you time out. So each of the state transitions is clearly marked in this state diagram. Similarly, we can extend the state diagram to have all the states marked here. And then it becomes fairly clear as to uh, where, how the states change and how we go from one state to another. So if this is in code, you would save the state variable in a enum possibly, and you would switch on that. So for example, if here we know that neutral can only go to group clicked when a group is clicked. So you just check that, right? If the group index is clicked, then you set the state as group clicked. Similarly, from group clicked, you can you'll either timeout, double click, or mouse drag to drag the group. So similarly, you will have these three conditions here. So this is a timeout, this is a drag, and this is a selection. So those would be the uh, three changes that your state can undergo. So as you can see, the code becomes a lot cleaner. It's much easier to understand what's happening, and it's fairly easy to build on, right? So if you want to add more states, you can just come here and figure out what that state is and where it would go, and from where it would come, and how it would interact with all of the others. And the only place you would have to update is this switch statement and figure out how to go to that state and where that state would take you. So those are the positives. The drawbacks is each state might have its own set of variables, and these would be stored globally or in some commonly accessible location. So for example, here the last group index, the last click ticks, etc., which are things that are stored in self, in this case in the application memory, and uh, they could theoretically be corrupted because other functions also have access to that, and also it just represents a mess of some sort, you can think about it, because there are far more variables than there need to be, and most of those variables would only be used in one or two states, uh, but even then they would have to be stored always. So the next way to improve on that would be to go to coroutines. So before even going to coroutines, let's just talk about stack memory. Like, what is the stack? So here we say it's the memory that a program uses to store data for function calls. Right? So that's the specific thing. If you've heard of stack and heap, then this is the stack that we're talking about. So if you're taking a simple example, here I have two functions. One is average and one is midpoint. So we want to find the midpoint of two vectors. So we calculate that by finding the average x value and the average y value. So this is not great code. You can obviously do it in much without so many function calls, but just to demonstrate, this works, right? So we start off by, this is the stack. Currently we are in the main function, and the main stores v1 and v2 and mid, right? So mid, it's going to calculate using the midpoint function. So we leave these as question marks. So now that you call midpoint, we're going to go to the midpoint function. So again, you'll see midpoint, A and B are going to be stored here. Mid is going to be what we return. So we'll initialize that to 0. And you have mid x and mid y. So first, again, mid x is a question mark, mid y is a question mark because you don't know what the values are yet. But this memory is already allocated. So once you look at mid x, then that makes another call. So then more memory is added on top of the stack, and this has these values, and we can quickly calculate, add a b. Now total is 50 divided by 2, and we return that, right? So now mid x is 25. So now once we want to call mid y, you can notice that we use the exact same memory again. The same chunk of memory is reused to calculate average again, and in case we are going to call some other function, it will still use this same memory. So this memory is temporarily used by this average function for the duration of its lifetime, and once it returns, it is no longer accessible to the program, right? So similarly, this a and this b value are not accessible from anywhere else in the program unless we explicitly send these values. So now we've calculated mid and we've returned it. So that is a very simple explanation of what this stack is. So now let's go to coroutines. So a coroutine is a function that can be paused and resumed. So again, let's take an example. So here, let's say we are within some kind of application or game, and when the rest button, whichever button that is clicked, we'll start a coroutine that says start resting for 1000 ticks. This start coroutine we'll go into later, but let's assume that there is such a function in the language or in your engine that can start a coroutine. So once you start the coroutine, this call will create a some memory on the stack, or will use some memory in the heap or in the stack wherever you allocate it specifically, and it will store these same values, right? So this looks very similar to the functions that we had called previously, but it's and it behaves in the same way as well, but the only difference is that it's not on the top of the stack. It's not right on top of the update call. It's somewhere else in memory which we know. So in Zig, for example, that would be stored in frame along with additional data of what the function needs. But the idea of a coroutine is that it's like a stack function, but just not at the head of the stack. It's stored somewhere else in memory, which could be in the heap or could be some other position in the stack, but most likely it would be in the heap. But that depends on your allocation strategy. So now this function is started, and we've set now as 0, and when we hit the suspend keyword, in some languages it's also called yield, in Zig it's called suspend, then this function gets paused and we return back to the uh, original caller function, but this state still remains. If you would have noticed in the previous case, when a stack function is returned, its memory gets cleared as well, or at least it gets marked as unused. But in this case, this memory still stays, and we know which is the point that we had suspended from. So then now let's call update again. Let's assume it's the one frame is passed, and then we're now in the new frame. Our coroutine is set, so we're going to resume the frame, which means we're going to resume the function. Since this was the point that we had stopped off at, the next line to be processed is this now is equal to milli timestamp, and so then the now variable in this function gets updated. So if you remember, this coroutine exists. This coroutine exists somewhere else in memory, not currently on the stack, but it behaves exactly like it was on the stack. So now again we'll check if rest ticks have passed. It's not yet passed. So then we'll loop and then go back to suspend and then continue the function again. So now some time has passed and then our ticks are higher. So now when we go to updating the now variable, the 1000 ticks that we wanted have already passed. So it's going to break and it's going to set the frame as null, right? So this is the frame that we were testing on. So now that this coroutine is completed, it's marking itself as completed. At least in this context, it's marking itself as completed, and uh, it's returning. So now this function is completed. So the next time we call update, this self.coroutine is going to be set null, and uh, this function is going to call work hard, which would probably be on the stack and have its own variables. So one thing to note here is that this coroutine had some memory allocated to it, but even on completion, it was not automatically freed, right? So this is memory that needs to be manually managed, at least in our implementation. There might be other places where it would self-clean up on its own. So now that we know what coroutines are, let's talk about how we use coroutines as state machines. So it's actually fairly straightforward. Whenever we change the state, we'll also start a coroutine that handles that new state. So in this case, group click mode, as you'll remember, there are three states. Either it will drag, it will select the group, or it will time out and go back to neutral, right? So again, here's the first case is that if there's a double click in time, it will start the coroutine called selected. Otherwise, it will start the coroutine called drag. In this case, it will break because the way we are using these states means that once you break, it will go back to neutral. So what are some of the positives of using this coroutines as state machines, right? So the first thing is that state variables are only stored where required. So for example, over here, this last click text is stored within this function. So it's stored within this memory. Like the way that start is only stored here. There's no other function that can update, or there's no way for this coroutine's start value to be changed from outside the function, which means that and also there is no space wasted for this same start within self, for example, or the application or the game. So this memory only exists for this context, and once this context is no longer valid, this can be cleared or gotten rid of, but it does not waste any additional memory. So suppose you have some states which require very little, I mean a lot of memory, but are required for very small, or a very infrequent basically, but they require a lot of memory to be stored. It means that you can save on some memory. Similarly, the changes between states are very clean. This is just the continuation of the fact that it's a state machine, and even the code is simpler to navigate and edit, again mostly by virtue of being a state machine. So some of the drawbacks are there is a certain amount of additional complexity. We'll have to manage the coroutines and their memory and things like that. Again, here they need to manually create it and manage. This is especially true in memory low-level languages where the memory needs to be managed. So you'll have to figure out when you can clear them, how to clear them, and make sure that the frames don't go out of context or the memory does not get reallocated, things like that. And even thinking like a coroutine takes some time. So to get the hang of using these, it might take some time to figure out exactly what is a coroutine, how it works, and things like that, and where it can be used. So these are some of the drawbacks for using coroutines for generating UIs. I mean, for managing UIs. So now we'll talk about how this was implemented. So here you can see that so this is the struct that stores the coroutine. This is all in Zig. So the frame, you would need a frame, you would need some data. That would be the data that this coroutine uses. The name is, I mean, mostly for debugging. Used and done are again for internal management. The main two things that you need are some way to access the frame and the data. So this is how I am creating new coroutines. So first I check all of the coroutines. If they are used, then I go to the next one. If they're not used, then I use that coroutine. Then we have to allocate data for this, as mentioned previously. This data needs to be allocated. So that's done here using these functions, and it's marked as used and not done. So whenever you want to call a coroutine, you have to use an async call, but before that you'll have to allocate some memory for it. These bytes are different from this data. There's just something to keep in mind. So both of these are separate things, I think. Okay, and these are the uh, parameters that you would call the function with, right? So you have to do at async call, and that's how you get to call it. So some of the common lines you'll find in the beginning of each coroutine is finding out what was the previous coroutine, and we use differ. So at the end of the coroutine, we set the previous coroutine active again, and we mark ourselves as done. This is done mostly so that we can clean up memory at some other point in the program. The memory cleaning is not done by the coroutine itself, it's done by one level higher, and marking it as done means that this can be used again once it's cleaned. Similarly, we set the active coroutine, we set our frames, etc., and start a infinite loop with the first thing being suspend. So some other uses for coroutines are for cutscenes. So this means that cutscene is in some sense a state machine that you go from, for example, scene 1 fade, scene 2, etc. So cutscenes, I mean coroutines are useful here. Similarly, timers and generators and iterators. What I mean here is, for example, if you have a so the example of using generators and iterators, one example would be for brute force solving. So for example, in my use case, I have a puzzle game where the number of possible solutions are in the order of magnitude of 7 or 8. So each solution takes up a certain amount of memory, right? So I have a coroutine called fill possible solutions within the application, and what it does is it loops through however and does whatever complicated processing to create solutions, and it appends them within a solutions array. And then if the solution is larger than a given size, it will pause, right? So in the brute force solver, first we start the coroutine. Then for all of the generated solutions, so let's assume there were a million or a million, it checks the solution, then it frees that data, it frees that memory, and then it resumes the coroutine, right? So then the coroutine comes back here and it maintains all of this state, right? So suppose we're using any combination of this, it means that it matters where in the loop we were for each of these cases. So storing all of this separately would have been a lot more complex to see how to continue to generate solutions, right? Theoretically it can probably be done, but this is a lot simpler because now this coroutine is maintaining its state for itself, and once it's suspended, it doesn't have to worry, you can say. So once it comes back, it will just continue generating without it making any difference, and once it's done, it'll set itself as null. So similarly, how many ever times we need to go and regenerate this, it can keep resuming the coroutine and then checking all of those solutions. So for me, what used to happen was, since there were so many solutions, my memory would get full, and like if there are 10 to the power 8 solutions, then memory gets full very quickly. And uh, once I broke that down into smaller chunks that can be processed separately, it all worked out. So that's another use for coroutines as generators and iterators. So here's, if you want more information on coroutines, you can look at Qt Framework by Randy Gall. So Randy Gall actually gave a talk last year, which was where I first heard about using coroutines as state machines specifically. And since then, he has published this framework, and he has, on this page specifically, there's a lot of information about how to use these, and that's where I learned all of this from. So the implementation that you've seen previously, that's all present in on my GitHub. And yeah, thanks for tuning in, and I hope this was useful.